In section 8.2, we're going to look a little bit at what unions and intersections of sets look like, and we'll also talk about odds. But I want you to look at some set theory here to get familiar with the notation. When we're looking for a union of two events, basically think of it as combining them together. That's what a union is, when you put something together. So this defines for any two events, you would see this for the symbol that represents we want to take A and B, combine them together. That means we would get the probability of something being in A, add the probability of something being in B, but if there is any place where they overlap, if there are any elements that are in both set A and set B, those are being counted more than once. This is if our events are not mutually exclusive. If it's possible to be in both of these sets at the same time, we've double counted if we just add the probability of A and the probability of B. So you have to be sure you subtract the probability that it's in both. And we'll look at some examples of this to make that a little more clear. Now, as long as the events are mutually exclusive and it's not possible for something to be in both set A and set B at the same time, then the probability of A intersected with B, which is this part right here, okay, has to be 0. If it's not possible for it to be in both, then that would be -0, which means there's no point in even writing it down. It just gives us the probability of A union B would be the probability of A plus the probability of B. So as long as you know they're mutually exclusive, that's all you're going to have to do. Now the complement we did talk about in the last lesson a little bit. It's oftentimes easier to find what it is that you don't want to happen and then subtract that from 1, because if you have accounted for everything that can happen in these events, then either it's going to be that event you're looking at, or it's going to have to be not that event. That there's no other option to occur. So that means if we take the thing we didn't want and subtract it from 1, that would give us the probability of the event that we're looking for. And that's what this is explaining here. We'll do some of these examples as well to help. And then odds. You oftentimes will hear, especially as it relates to maybe sports and betting or horse races or whatever, they'll give you odds of a team winning or a horse winning. And usually odds are expressed something like 3-to-1 or, even odds, 1-to-1. So the way those are written, you would put down the probability of the event happening divided by the probability of the event not happening, if you're talking about odds being in favor of an event. Now, if you're talking about odds being against an event, then that fraction switches, and you would put the probability of it not happening over the probability that it would happen. So you've got to make sure you remember we're not giving just the probability that something would occur. Like, for example, if I said, what's the probability of getting heads when I toss a coin? Well, I've got one outcome that would be heads out of 2 possible outcomes, because it could either be heads or it could be tails. So my probability of getting heads is 1/2. But if we were talking about the odds of getting a heads, that would mean I've got one outcome that's heads compared to one outcome that's not heads. My odds would be 1-to-1. Okay, so make sure you don't get confused on the difference between those. Odds is different. Now, a container contains 7 red balls, 4 green balls, 9 white balls. A single ball is drawn at random from the container. Let's first find the probability that the ball is red. Now, if we want the probability the ball is red, how many red balls are in the container? Well, there are 7. Out of how many balls are in the container altogether? If I were to add up 7 plus 4 plus 9, I get 20. So the probability the ball is red is 7 over 20, which is about 0.35. 35% would be another way I could express that probability. Remember, probability is always a fraction or a decimal number that's between 0 and 1. Always when it's probability. Odds will not be that way, but probability will. Now, look at B. The probability that the ball is green or white. Keep in mind, when I see or, that's telling me to add. So the probability that it's green plus the probability that it's white. Now, let me just ask the question. Can the ball be both green and white? The answer is no. We don't have any indication that there are any balls in there that are not solid color balls. So that means these are mutually exclusive. I don't have to subtract the probability of being green and white because there isn't one in there that's green and white. So the probability of a ball being green is 4 over 20. Plus the probability of a ball being white is 9 over 20, which gives us 13 over 20 for our probability, which is 0.65. Now on C, the probability that the ball is not white. Okay, I can do this one of two ways. I can either calculate from reading the problem, if it's not white, that would be taking the probability that it's red plus the probability that it's green, or I could do 1 minus the probability that it's white. That's finding the complement. And the probability that the ball would be white is 9 out of 20. So if I get a common denominator, I'm going to write 1 as 20 over 20 minus 9 over 20, and that gives me a probability of 11 over 20, which is 0.55. So either one of those would be acceptable answers for the ball is not white. Now to find the probability the ball is not red, we can do the same thing. We can do the complement, 1 minus the probability that it is red, because we've already calculated the probability that it's red. We did that back on A, and we had 1 minus 0.35, which means we're going to get 0.65. And that is perfectly acceptable to use work that you have done in a prior part of the problem. You don't have to regenerate the information you've already found. Let's go to the next example. So now let's look at a Venn diagram that's going to show you a sample space. In this case, we have elements that are in circle A. We have elements that are in circle B. There's an area where they overlap. And then we have a certain number of elements that are just in the sample space, but not in either circle A or B. So if we are looking for the probability of, now look carefully at how this is written, we want A intersected with B, but then notice there's the complement sign. So we want everything except A intersect with B, or everything but not where A and B intersect. And when it's a complement, remember our easiest way to compute that is to do 1 minus the probability that it is in that intersection. So, looking at our diagram, how many elements are in the intersection of A and B? There are 20. Divided by the total number of elements in the whole diagram, I would add up all these pieces. 40 plus 20 is 60, plus 25 is 85, plus another 15 is 100. So we're going to have 1 minus 20 over 100, or you could say 1 minus 0.2, which means 0.8 or 0.80. That's the probability that you are not in the intersection of A and B. Now, we're back to rolling die, and we're going to look at probabilities of coming up with these things like we just did in the last section. So I think the only ones, just to save a little time, that we might do would be look at E and F. We actually have some new ones with the or, and then there's an and. I'm going to draw that grid again, 6 rows, 6 columns, and we'll write those sums in here. So 1, 2, 3, 4. I know it takes a little time to set this up, but it does make it a lot easier when you go to answer these questions. So we know 1 plus 1 is 2, and then we count up by 1 the rest of the way across the top row. 2 plus 1 is 3, and so we count up by 1 on that row. Then we start with 4. So I'm going to get this all filled in. And we'll answer just a few of these. We won't do all of them, but it really wouldn't be that difficult once we have this drawn out. And then our bottom row is 7, 8, 9, 10, 11, and 12. Okay, let's look at A. The probability that the sum is 4. Again, we look for the diagonal where 4s show up. And the probability that the sum is 4, I see 3 of those out of 36, because remember there are 36 in all inside our grid, and that would reduce down to 1/12. That's our probability. Let's do C. The probability that the sum is not 4. Remember, when I see that word not, think complement. So that means it's 1 minus the probability that it is 4. And we just calculated the probability that it's 4. So that was 1/12. And 1 minus 1/12 would be 11/12. Okay? If we look at E and we want the probability that the sum is 6 or 11, remember or means add up. So the probability that the sum is 6, if I count up the 6's, I have 1, 2, 3, 4, 5. So 5 out of 36 is the probability that I get 6. Now the probability that I get 11, here's the only place 11 show up. There are 2 of them. So 2 out of 36. If I add those together, I get 7 over 36. And that's what I'll come up with. Now, what about the probability that the sum is 6 and 11? Now think about that for a minute. It's asking you, when you roll 2 die, what's the probability that when you add them up you get 6 and you also get 11? Can that happen? The answer is no. On any roll, when I roll those die and I add them up, I'm going to get one number. I can't get 2. The probability of that happening is 0. It's impossible. I can't add them up and get 2 different numbers. And then the probability that the sum is divisible by 3 and 4, we would have to stop and think which numbers would be divisible by both 3 and 4. Now the only numbers we see in the table are anywhere from 2 up to 12. So the only number that would be divisible by 3 and 4 has to be this one right here, 12. And that means I have only 1 out of 36 that would be divisible by both 3 and 4. Now look at this table. A class is made up of 4 male and 5 female seniors, 3 male and 6 female juniors, and 2 male and 5 female sophomores. So we're going to use this chart and we're going to answer these questions because we're going to pick a person at random to serve on an advisory committee. What would be the probability of choosing a male or a junior? Now, here's what that's asking us. We need the probability that we get a male. Or means we're going to add. So plus the probability of getting a junior. But then you have to ask yourself, is this mutually exclusive, or is it possible that I could get a male who is also a junior? And the answer is yes, you can. So you need to subtract out the probability that it's a male and a junior. Okay, so let's see what we come up with if we look at this table. Now, the probability of it being a male, here is where male shows up. It's this row. And if I go all the way to the end, I come up with 9. So there are 9 males out of, now if you look at this bottom row, it tells you there are 25 total students. Okay? So the probability of being male is 9 out of 25. Plus, the probability of being a junior, here's my column where the juniors were counted, and there are 9 that are juniors. So that's 9 out of 25 who are juniors, but I've got to go back and look to see how many were both male and junior. So I need to see where these two intersect, and it's this right here. There were 3, so I've got to subtract out 3 over 25 from this. So if I add all this up, 9 plus 9 is 18. 18 minus 3 is 15. And 15 divided by 25 reduces down to the fraction 3/5, which is 0.6. So it's about a 60% chance that randomly picking a student, it would either be a male or a junior. Now, let's see about choosing a female sophomore. Well, that's only choosing one thing. I just need to look at the table to see how many are female sophomores. So I've got to look for the box where female and sophomore intersect. So female sophomore, that's right here. There are 5 out of 25 students who are sophomore females, which reduces to 1/5, which is 0.2. So it's about a 20% chance that I get a female sophomore. All right, probability of not choosing a senior. Well, that sounds to me like that might be a complement question. If we did 1 minus the probability of choosing a senior. So let's see if we see what the probability of choosing a senior actually is. Looks like there were a total of 9 seniors out of 25 students. So 25 over 25 minus 9 over 25 gives us 16 out of 25, which is about 0.64. You got about a 64% chance of not choosing a senior. Same concept on not choosing a male. I could do 1 minus the probability of getting a male. So if I look at my chart and I follow across, there were 9 males out of 25. Remember, we actually saw that back up here on A. If I calculate that out, that's the same thing we just got on the one above. That's 16 over 25, which is 0.64. And that's sort of a coincidence. Don't automatically assume that's going to happen. Just so happen those numbers happen to be the same. Now, if I want to get the probability of choosing a female or a sophomore, remember the or tells me I'm adding things up. So the probability of getting a female or means plus the probability of getting a sophomore, but then you have to ask yourself the question, are they mutually exclusive? Can I have sophomores who are female? And the answer is yes. So I've got to subtract out the probability of being a female and a sophomore. So looking at our table, I need a little more space. What we're going to see is the probability of being a female is 16. It's this number right here because I had to follow the row all the way across. So I've got 16 out of 25 is the probability of being female. Now the probability of being sophomore, that's this number right here. 7 out of 25. But we're going to subtract out the probability that you're female and sophomore. And looking in the table, or if you look back at B, we actually found it there. That was 5 out of 25. So let me pull up a little bit so we've got a bit more space. And 16 plus 7 is 23, and 23 minus 5 would give us 18. So 18 over 25 means we've got about a 72% chance of either choosing a female or a sophomore. And then the last one says choosing a senior or a female. So we'd need the probability of a senior plus the probability of a female, but we've got to remember there's always the chance. In fact, it's not just the chance. There are some students who will be seniors and female. So if we look back, the probability of being a senior, we actually found that back in C, if you look right here, but you can go back and you can look at the table. That was 9 out of 25 students who were seniors. Now, the probability of being a female, we actually found in E. That's right here. The probability of being female was 16 females out of 25. And then we need to subtract out the probability that they are a senior and a female. Now, let me pull back up to the table for a second. So the probability of being a female and a senior looks like that's got to be right here, this 5. So that means 5 students out of these 25 were both females and seniors. So if I calculate that, 9 plus 16 is 25, 25 minus 5 is 20. We have 20 out of 25, which is 80%. And let's go to the last page. A candidate for mayor of a small town predicts that he has an 80% chance of winning the election. Now, if he's predicting he has an 80% chance of winning the election, what would you say is the probability he would lose? Well, the probability that he would lose has to be 1 minus the probability that he would win. That's a complement question. And since his probability of winning is 80%, 1 minus 0.8 gives us 0.2. So he's got a 20% chance of losing. Okay? But let's take this now, convert it into odds. What are the odds that he would win the election? So we want to take the probability that he wins and compare it to the probability that he loses. So what I would suggest is, since we've got an 80% chance of winning, a 20% chance of losing, okay, you could think of it this way: 80, put your colon, and a 20. Sometimes you can write it as a fraction. You may see it that way, but most oftentimes you see odds written with the colon separating them. And then think about it as reducing a fraction. If I had 80 over 20, that would reduce down to 4 over 1. So it's 4 to 1 odds that he's going to win. Okay? If you saw that in fraction form, it would look like that. So either of those two would be acceptable, but the colon is the more common way to write odds. Now, what if I ask the question, what are the odds that he would lose the election? That would mean that we would have the probability that he loses compared to the probability that he wins. Our numbers don't change from above, but the order they're written in will change. And that means it's a 1 to 4 set of odds that he's going to lose.